Hi everyone, welcome to your lesson on enthalpy of combustion as part of week 8, day 2 of your learning in higher chemistry. So today we're starting on the chemical energy topic of unit 3b, which for the first part of the topic that we're going to do today has parts that you'll recognise from your work at National 5. But later on in the topic, there's going to be some new aspects of chemical energy that we'll learn about too. Okay, so the learning outcomes that we're going to cover in this video can all be found in your Unit 3B booklet in the chemical energy section. So that comes after the getting the most out of reactants section that we've just completed. So there's quite a lot of learning outcomes that we're going to cover in this lesson, but as I said, quite a lot of this we've done previously at National 5, so there is going to be a bit of revision as part of the learning that we do today. Okay, so we're going to start with an introduction to the chemical energy topic. So thinking about what chemical energy is, and why we need to consider the energy of chemicals and in chemical reactions. So when we look at any chemical reaction, we know, thinking back to the rates topic, we talked a bit about this as well, but we know that when a chemical reaction takes place, we need energy to break the bonds in the reactants. So energy needs to be put in for those bonds to be broken, but we also get energy back when new bonds form in the products. So some energy has to go into the reaction, but we also get some energy back out. And there's a little diagram here just to illustrate that. So when we look at the kind of overall energy in a chemical reaction, we always find that there's a change in the energy during the chemical reaction. So depending on how much energy is needed to break the bonds and how much energy you get back when you make new bonds, there's going to be a net either gain or loss of energy. The energy will never be the same. Overall, there'll always be a change in the energy. So if we have extra energy left over, then that energy will be released and we get what we call an exothermic reaction. And if we have less energy than what we need to break those bonds, then we're going to have to absorb some energy, and that's what we know is called an endothermic reaction. Okay, so you should be familiar with the terms endo and exothermic from National 5 and also earlier in higher when we've looked at the controlling the rate topic. So this should just be a little bit of revision and just making sure you're quite confident on those terms. Okay, so we've got some notes to take down on this slide here. When we talk about chemical energy, we normally refer to it as being enthalpy. So that's just another word for chemical energy. And as we saw in the previous slide, every chemical reaction involves some form of enthalpy change. So some form of change in energy. And we should recognise the symbol for that, delta H, which we have seen previously when we looked at the controlling the rate topic and being able to work out the enthalpy change or delta H for a reaction. So we can do that by looking at potential energy diagrams, working out the difference in enthalpy between the products and the reactants is one way of working out the enthalpy change, but we're going to see that there's more ways of doing that in this topic. Okay, so a little recap on our key terms. An exothermic reaction, is one that releases heat energy. And remember what that means is the value of delta H, the enthalpy change, is going to be a negative value. and that represents the fact that energy is being released. An endothermic reaction is the opposite, so it absorbs heat energy and it has a positive delta H, and that's representing the fact that energy is taken in during the reaction. Okay, so we've just finished looking at the getting the most from reactants topic earlier in Unit 3B, so you were looking at some gas calculations. But at the start of that topic, we were thinking about chemical processes. So thinking about what actually happens in the chemical industry, what steps are required, what processes are involved in trying to manufacture a particular chemical. So we had to look at kind of all the things that need to be considered when chemists are trying to set up a new chemical process. And one of the things that has to be considered is the energy involved in the process that you're trying to do. So we have to be able to predict what kind of enthalpy change is going to be involved in our process. Not just whether it's going to be ex or endothermic, that needs to be considered, but we also need to be able to work out the kind of exact quantity of energy involved. And there's several reasons why we need to be able to do that, okay? So if you think about an endothermic reaction, that reaction is going to need energy to be supplied to it. If it is having to absorb energy, then we're going to need to supply that energy from somewhere. So if we have an endothermic reaction, we might have to heat it in order to give it extra energy to keep the reaction going, which is going to have a cost associated, and that's something which is very important in chemical processes, is working out the costs involved and making sure that your process is as cost effective as it can be. Because it's a business, at the end of the day, it's about making money. Okay, so if we've got an endothermic reaction, we need to think about the cost of supplying it with energy. If we've got an exothermic reaction, they generate their own energy. So that reaction is going to produce energy, which means you might have to give it a little bit of heat to start it off, but once it gets going, it'll be able to generate its own heat, which seems good. But the issue with exothermic reactions is they can get out of control. So if the reaction keeps on producing more and more and more and more heat, then that can get to a dangerous level. So it's more of a safety reason when we think about exothermic reactions. We might need to keep a close eye on them. They might even need to be cooled down. So again, there's a cost associated with that. And that's to make sure that the temperature stays at a safe level. Because if the temperature goes too high, lots of things can happen. You can get different reactions taking place that you don't want to happen. And you can also get potentially a thermal explosion happening because the reaction just gets too hot. Okay, so you do need to have an awareness of why chemists need to be able to work out enthalpy changes in the chemical industry, and these are the main reasons, thinking about our two types of reactions. Okay, so make sure you've got those noted down. Now, as we said, we need ways of predicting the enthalpy change. So there's different ways we can do this. If you've got a huge industrial process involving tons and tons of chemicals, you don't want to have to use all those chemicals in order to work out what the enthalpy change will be. So what chemists will do when they're designing a process is they'll do a small scale experiment. So they'll do the same reaction, the same process, same conditions, but with much smaller quantities of the chemicals. They can carry out that reaction, carry out those experiments, and work out the enthalpy change for that reaction, and then scale that up to represent the larger quantities that would be used in reality. So there can be some experimental work involved in working out the enthalpy change, and that's something we're going to look at in today's lesson, is one way that we can do that. But it can also just be a numerical calculation. So there's lots of data that exists on chemicals, as you'll have seen in your data book, but there's far more than what's in your data book even. So there's lots of calculations that could be done without doing any extra experiments, just using existing data in order to predict the enthalpy change for your particular reaction. So again, later in the topic, we're going to have a look at some of those calculations that we can do that don't rely on an experiment, but just use data that's already out there in order to work out the enthalpy change. Okay, so there is quite a bit of calculation work involved in this part of the topic, and a little bit of theory to go with it as well. Okay, so one of the experiments we can do, or one of the things we can work out for a reaction is what's known as the enthalpy of combustion. Okay, so combustion reactions, burning a substance, reacting it with oxygen, they're really, really common chemical reactions, and they're fairly simple to carry out in the lab as well. So if we can do an experiment to work out the enthalpy of combustion of a substance, it can help us with other enthalpy change calculations as well. We might just be interested in the enthalpy of combustion, but it can also help us with other calculations. Okay, so we're going to start with a definition of what we mean by enthalpy of combustion, which is the enthalpy change when 1 mole of a substance burns completely in oxygen. So that's a reaction we're familiar with, combustion. So we've looked at this at National 5 for hydrocarbons, like propane in this example. The hydrocarbon reacts with oxygen and forms, if we're talking about complete combustion, which the definition does, then it forms carbon dioxide and water as the two products. Okay, so you should be able to write equations for combustion reactions. We've been doing that since National 5, so knowing those two products. And you should also be able to balance them. And when we're talking about enthalpy of combustion, the really important thing in the definition is that it's for 1 mole of the substance that we're burning. So when we've balanced this equation, we're keeping only 1 mole of the propane, and we're balancing the equation using all the other substances if required. So when you write an equation for enthalpy of combustion, or when you see an equation in a question, it'll always be written for 1 mole of the substance. And that's not by accident, it's because that's part of the definition. Okay, so every enthalpy of combustion will have a value associated with it. Lots of those values are calculated. Some of them are in your data book, but there's lots of other ones that they're out there and calculated. But it's being calculated through experiments. And we'll take a wee look at what kind of experiments we can use to do that. And just before we do, when we've written this delta H value, you'll notice that it's got a negative sign in front of it. So that is to represent the fact that it's an exothermic reaction. So we're talking about combustion, which is releasing energy. So when you give a value for enthalpy of combustion, which is something you can be asked to do, you have to remember that it must have that negative sign in front of it to represent the fact that it's exothermic. And as I was saying before, remember that the equation must be for 1 mole of the substance that you're burning. Okay, it can be any number of moles of the other substances, as long as it's 1 mole of your fuel, the substance you're burning. Okay, so the experiment we would use to work out enthalpy of combustion essentially involves us taking a fuel and burning it, and in some way measuring the energy that is released. Okay, so this is an experiment that you should be familiar with from National 5. We looked at this as part of Unit 2 in the Energy from Fuel section of National 5. And it's this sort of setup in the diagram. So it's where you've got maybe a spirit burner, or alcohol burner as it's called here. Other burners can be used depending on what fuel you're investigating. We use a metal can holding some water. So when we burn the fuel, the heat is transferred to the water, heats up the water, and then we can track the temperature of the water throughout the experiment. Okay, so there's quite a lot of measurements. In order for us to do a calculation with this data, we need to take quite a few measurements. We need to make sure we record and we know the volume of the water that's being heated. So that's an important part of our calculation. We need to know how much fuel, how much of the substance has been burned. So we've got to get the mass of the burner at the start and the end of the experiment. And that's important when we think about working out our value in terms of 1 mole. We didn't have to worry about that in Nat 5, but we do have to do that higher. So that's an extra part of our calculation that we'll look at. And we also need to record the temperature of the water. So we need to know the start temperature and the end temperature so that we can work out how much the temperature has changed. Okay, so it's all very similar in terms of the data we need and the setup to what we saw at Nat 5. If you would like a little reminder of the experiment and how to set it up, then at this point you can pause the video, and there's a link in the slides where you can go to another video and watch a little clip of this experiment in action. Okay, when you're finished, come back to this video and watch the rest of the lesson. Okay, hopefully you enjoyed that little video clip of the experiment. You should remember doing something very similar when you did National 5. So we can do these sorts of experiments for whatever substance we're trying to work out the enthalpy of combustion of. And then once we've got the data that we needed to collect, then we can do a calculation with that data. And part of that calculation involves us working out the heat released when our fuel is burned. And that is a calculation, again, we should be familiar with from National 5. So it's the same calculation that we did when we looked at the experiment back in Nat 5, which is an equation that lets us work out the heat released from burning a substance. Okay, so the equation I'm talking about is EH equals Cm delta T. That equation is in your data book on the first page with all your formulas. Remember the different parts of the equation. So everything in the equation is to do with water. It's nothing to do with the fuel that we're burning. That's going to come into our calculation later. So all the values we put in are to do with the data of the water. So C is a constant, which represents the specific heat capacity of water. And that value is in your data book. It's 4.18 kilojoules per kilogram per degrees Celsius. That's exactly the same as we had at Nat 5, still the same value. The M represents the mass of water. So we can work out the mass of water from the volume of water that was used in the experiment. Because the density of water, 1 cubic centimetre of water is the same as 1 gram. So if you know the if you know the volume of water in cubic centimetres, then that's the same as the mass in grams. One thing to be careful with is we've got to have that in the units of kilograms. So if you've got 200 cubic centimetres of water, then that would be equivalent to 0.2 kilograms of water. So just dividing by 1,000 if you've got the quantity in grams or cubic centimetres. Okay, and then the final part is delta T, so the temperature change, and that will either be worked out for you in the question, or you'll have the start and end temperature in order to work it out yourself. Okay, so at Nat 5, this was all we did. We took the data from the experiment, we put it into this equation, and we worked out the value for the heat released. And that was for whatever quantity of fuel was burned in the experiment that was done. If we're working out enthalpy of combustion, which is what you'll be asked to do at higher, then we know that enthalpy of combustion represents 1 mole of a fuel. So we have an extra step to our calculation now at higher. But once we've worked out the value of the heat released, we're going to have to scale that value up to represent us burning 1 mole of our fuel. Okay, 1 mole can be quite a big quantity of fuel to burn. So rather than burning 1 mole and waiting to see how much heat's released, then we'll burn, in most experiments, a smaller quantity is going to be burned, and then you'll be able to scale up the value from your calculation. Okay, so it is a very similar calculation to Nat 5, but it does have that extra scaling step involved that can make it a little bit trickier. Okay, so what we're going to do now is have a look at some example calculations where we're being asked to work out the enthalpy of combustion. Okay, so let me move myself out of the way. In the box at the top of the screen here, you've got your question. So make sure you note down the example question that you've been given here. We're being told, that when 3.6 grams of butanol was burned, 134 kilojoules of energy was released, and we are to calculate the enthalpy of combustion of butanol in kilojoules per mole. Okay, as we're going through this calculation, remember you can pause the video so that you have time to write down the notes, and then just start again when you're ready for the next step. Okay, so this question has actually done some of the work for us. So they've already told us the value of the heat released. They've told us that when we burned this mass of butanol, we got 134 kilojoules of energy released. So we don't actually have to use the EH equals CM delta T equation in this particular question. And this will happen sometimes, quite often it happens in a multiple choice question, but it can happen in section 2 as well. If you didn't realise, you're looking at this question and you try to use the EH equals CM delta T equation, you'll very quickly have issues because you don't have any of the data that you need. So you don't have the mass of water, you don't have a temperature change. So that should give you a clue that part's not required. Okay, so we've got a value for the energy released when we burn 3.6 grams of butanol. So all we need to do is scale that up to represent 1 mole. So the first thing we're going to do, step 1 of our calculation, is to work out the GFM of butanol, the substance that we're burning. Okay, so just exactly as you would do for any other substance, get your values, your relative atomic masses from the data book, add them all together. For butanol, that works out as 72 grams. So now we know the mass of 1 mole of butanol. We're going to be able to use that to scale up from the mass that we've actually burned. Okay, so step 2 is just a simple proportion calculation or scaling, starting with that relationship that the question's given us. So we know that 3.6 grams of butanol produces 134 kilojoules of energy. So we can scale that. The first step I've done here is to just scale that back to 1 gram. You don't have to write this interim step out. You can go straight to 72 if you're confident. But for anyone who's less confident, work out what 1 gram would be first of all. So if we divide both sides by 3.6, that gives you 1 on the left hand side and 37.22 on the right. And then we're going to bring in the GFM, because we don't want to work out what 1 gram produces. We want to know what 72 grams or 1 mole produces. So we're then going to multiply both sides by 72 to get our final answer of 2,680. Now, this is not where your working is finished. If you leave your answer as 2,680, or if you leave it like that and you stick kilojoules per mole on the end for a unit, you are not going to get full marks for this question. Okay, that is the number that's going to come out of your calculator. But what you have to remember is that you're working out an enthalpy of combustion value. So when you give your final answer, you need to put the negative sign on the front of that number, because enthalpy of combustion is a release of energy, so it's minus 2,680 kilojoules per mole. Okay, that negative sign is really, really important. You have to remember to put that in, or you will not get full marks. Okay, so it's always a good idea with enthalpy of combustion to kind of write out a final step of your working, where that's going to remind you to put that negative sign in. Okay, so let's look at another example. I'll move myself out the way again. So if you take a note of the question, this time we've got 0.16 grams of methanol being burned in a spirit burner, and temperature of 100 cubic centimetres of water is raised from 20 degrees to 27 degrees. And we are to calculate the enthalpy of combustion of methanol. Okay, remember, pause the video if you need a bit more time to copy down the question. Okay, but you can see this question is different to the previous one. So they haven't given us a value for the heat released. They have told us the volume of water, and they've told us start and an end temperature. So that should be your clue from the data in the question there, that you're going to have to start by working out the heat energy released. And more often, I would say, when you're looking at section 2 questions, you're going to have to start with working out the energy released. Okay, that's usually going to be your first step. As I said in the previous example, multiple choice questions, that will usually be done for you, and the occasional section 2 question, but most of the time you're going to have to start with heat released. So, all of the information, except for our constant for working out the heat released, is in the question for us. So this first step should be very familiar to you hopefully from Nat 5. So we're going to use EH equals CM delta T. If we just pick out the data that we're going to put into the equation, so we've got the value of C 4.18 from the data book. That is, I believe, it's at the back of your data book for the higher data book rather than on the first page with the equations. I could be wrong, but I think it's at the back of your data book. So if you can't find it, look at one of the pages towards the back. There's quite a lot of constants in there, and you should find the value for C if it's not on the first page. Yep, so the value for C, the value for M is going to be 0.1 kilograms. So that's coming from the fact that we've used 100 cubic centimetres of water. So just converting that into kilograms, dividing by 1,000 to give us 0.1. And delta T, just working out the difference between the two temperatures in the question. So 27 minus 20 to give us 7 degrees. So then we're just going to put those numbers into our equation. So it's going to be 4.18 times 0.1 times 7, and that gives us 2.926 kilojoules. So that is the amount of energy released from burning the 0.16 grams of methanol. As I was saying to you earlier, at Nat 5, this is where our calculation would have stopped. But for enthalpy of combustion, we know that we have to scale this up to represent 1 mole. So we're now going to follow the same kind of steps as we did in the first example. Now that we've got our value for the heat released, we're going to scale that up to represent 1 mole. Okay, so starting with working out our GFM for methanol, which is 32 grams. And then we're going to do our scaling step, our proportion. So we're going to take the relationship, partly coming from the question, so 0.16 grams was the amount of methanol that was burned, and adding in the value that we calculated for the heat released. So 0.16 grams produces 2.926 kilojoules, and we're going to scale that to represent what 32 grams would produce. So again, you can do the interim step if you like. Scale it to 1 gram. So divide both sides by 0.16. And then scale it up to 32 grams. Or you can do that all in one step if you're quite comfortable with that calculation. And what you'll get as final answer should be 585.2. Again, don't leave your answer here, because we've got to put that negative value on the front. Okay, so the enthalpy of combustion is minus 585.2 kilojoules per mole. Okay, so we've had a look at a couple of example questions working out enthalpy of combustion from different starting data. So you should, as I said, be fairly familiar with the EH equals CM delta T part from Nat 5. Perhaps just needed a little kind of refresher of it because we've not used it for a while. And then the rest of that calculation is just working out GFMs and using proportion or scaling. Okay, so they're all skills that we should already be quite comfortable with, and it's just knowing how to apply them in this type of question. Okay, you're going to get lots of practice of these calculations in lesson 2 today, so you should be feeling nice and confident with them by the end of your work today. Okay, so the final thing we need to look at today, thinking about our enthalpy of combustion experiment, is looking at the experimental setup that we use and the apparatus that we use. And again, this is something you might remember a little bit about from Nat 5. So when we, if we were to look at that previous value for the enthalpy of combustion of methanol, it's 585.2 minus 585.2 kilojoules per mole. That value, if you were to look up the enthalpy of combustion of methanol in your data book, that value is probably a lot less than what the data book says it should be. And that is typically the case when we do experiments in the lab to try and work out enthalpy of combustion or try and work out the heat released. We usually get much lower values than what we should do. Okay, so when we compare them to values in the data book, they're going to be lower than what the data book says. And it's because of the apparatus we're using and the setup that we have. We're limited in the lab with what we can actually do. And This is kind of the best version of the setup that we can possibly come up with. So we've got our metal can, we've got our spirit burner, and we've added a draft shield down the sides, which is to try and keep the heat being released from the fuel, try and kind of funnel that towards the water in the beaker, okay? Because this whole method is relying on that heat that's released, which is released in all directions from the flame that's burning. We're relying on that heat going up to the water because we're measuring the temperature of the water. And that's our only way of tracking the heat that's released. So if any heat doesn't go into the water, then that's going to affect the value that we get, and it's going to mean that the value we calculate is lower than what it should be because we're not tracking some of the heat that's released. So even if we do this setup and we add the draft shield to it, we're still going to have issues with the setup we're using. And there's two main reasons why we're going to get lower values and we're going to have issues with this setup. One of them is because incomplete combustion is going to be taking place. So we're not burning our fuel in a plentiful supply of oxygen. As soon as you see little orange flecks appearing, or an orange colour in the flame, then that is signifying incomplete combustion. And there won't, just from burning in the air, there won't be enough oxygen for all the fuel to burn completely. And the problem with incomplete combustion is it's not as efficient. It doesn't release as much heat from the fuel as complete combustion does. So if we're getting incomplete combustion taking place, then we're getting less energy released from our fuel. And that will be happening when we burn our fuel in the open air. Okay, the other reason is what we're trying to prevent with the draft shield, but we're not entirely successful with, is heat being lost to the surroundings. So even with that draft shield, we're going to minimise heat loss to the surroundings as best we can, but some of it is still going to escape because the draft shield is not going to cover the flame on all sides. Okay, so again, any heat that's lost doesn't go into the water and therefore doesn't get counted in our calculation. So, in industry, there is a more sophisticated version of this experiment that can be done with different apparatus, and that's what's used to calculate the values that are in the data book. It's known as a calorimeter, or maybe a bomb calorimeter, it's sometimes called. And this setup, there's a diagram of it here. You do not have to copy this diagram, but make sure you copy the notes that are going to come beside it. But in the diagram, you can see that it's quite different. You've got essentially a big box that you're... Oh, sorry, it was a fly. You've got a box that your experiment's taking place inside, and then there's a beaker inside there, a container with water, and then there's another box inside that, which is where the fuel is actually being burned. So right in the centre here we've got our fuel, and there's little wires to ignite the fuel. And you'll see the tap here is for oxygen. So inside this inner container, we've got an atmosphere of pure oxygen. So our fuel with the calorimeter setup is burning in pure oxygen. So that should eliminate any issues of incomplete combustion, because if we've got pure oxygen, then we're going to get complete combustion happening only. Then the other thing that we can note is the fact that the water is basically surrounding that container where our fuel is burning. So you can see we're looking at a cross section of it, but that container is inside and then there's water all around it. So when the fuel is burned, the only place that the heat can go is out into the water, because there's water on every side around where it's burning, so it has no other place it can go except the water. So both of those features mean we get a much more accurate value. So we're using pure oxygen, meaning that we get complete combustion instead of incomplete, and we've surrounded the fuel with the water that we're trying to heat up, so we're not having any issues with heat loss. Okay, so you may see, again, similar to what you saw at Nat 5, you might see questions comparing these experimental setups and asking you for advantages, disadvantages of them, or maybe even to suggest or explain what the problem is with a particular method or with the lab method. So make sure you're aware of what the two setups kind of do, the differences between them, and remember your two important points about how much oxygen there is, whether it's complete or incomplete combustion that's happening, and whether you're getting heat loss or not. That's the two things that are really going to impact on your value for the enthalpy of combustion. Okay, so we've covered all of these learning outcomes. So we've talked about the definition of enthalpy, exo and endothermic reactions, talked about why it's important that we can work out the enthalpy change of a reaction for the chemical industry, and we've looked at the calculation of enthalpy of combustion, so using heat, the calculation of heat released as part of that, but also examples where we're just doing the scaling part to 1 mole. Okay, when you are finished working through these notes, you might want to have a look in your Unit 3B booklet. You might have already been using that or had it in front of you while you were working through the notes, but you can go to the learning outcomes and at the end of the lessons today, after you've done lesson 2 as well, do a little self-assessment using the smiley faces of how you feel about each learning outcome. There's also some notes in the Unit 3 booklet. The pages are listed in the instructions video, where you might want to go and highlight some of the key notes in your booklet as well as what you've taken a note of in your jotter. And you're going to move on after your break in lesson 2 today. You're going to be using the booklet to do some practice questions on what we've learned about this lesson. Okay, so when you move on in lesson 2, make sure if you have any questions, go onto Teams and ask me or Mr. Shepherd if you're looking for any help. And there will also be solutions to the questions that you're working through that you can use to self-mark your answers as well. Okay, and when you're finished lesson 2 today, remember to upload a photo of the questions that you've managed to work through so that your teacher can have a look at how you've gotten on and give you some feedback on any issues that you've had. Okay, I hope you've enjoyed your lesson today, and we'll see you next time. Bye.